Hello, my name's Dave Minturn from Intel, and my co-presenter is Anil Vasudevan. Today we're going to be talking about tuning and optimizing Ethernet-based NVMe over fabric transport protocols. The agenda for the talk is we'll start with a review of the NVMe over fabric Ethernet transport protocols, and then we'll move into to talk about the host side CPU efficiency and then move into the target side efficiency, and then conclude with a summary. Some of this material was shown last year, and you'll note that we put a reference to last year's presentation for review. So the transports, NVMe over fabric transports for Ethernet, there's actually two of them defined. What I'm showing here is RDMA and TCP. RDMA covers the variants of types of RDMA. For example, iWARP and RoCEv2 are all under the RDMA, NVMe over fabric RDMA transport, and then NVMe over TCP is the other one. If you look at the layering for the NVMe over fabric transports, what you have at the top is the NVMe layer, and this is common across all transports for NVMe. You have a host and you have a subsystem. Subsystems commonly referred to as targets, so that's sort of analogous. And underneath that abstraction NVMe layer, you have the transports, which are used to carry the NVMe commands and completions in what they call capsules. So for Ethernet, again, what you see on the left in the orange is the NVMe over RDMA, and then on the green is NVMe TCP, and that's the exchanges are done between the host side and the target side. As you drop down, you see RDMA verbs is how the RDMA layer talks to the hardware down below, down into the network layer. TCP sockets is for the TCP transport, and you'll note that in the RDMA, the two variants of RoCE and iWARP, one being UDP on lossless Ethernet, the other being TCP on regular Ethernet. That's pretty much what you see from the network layering and the difference between them. Okay, if you're looking at sort of a comparison, we put this chart together to sort of enable folks to determine like which one of these protocols would be suitable for for your data center deployment. If you look at NVMe over TCP, looking at the network infrastructure requirements, what you see is that standard NICs and standard Ethernet switches, because it's based on TCP. As you move over to the right, you look at NVMe RDMA with iWARP in that case, and you have RDMA enabled NICs, and because iWARP is a TCP-based RDMA protocol, you have standard Ethernet switches that could be used. Moving over to RoCEv2 RDMA, again, it's RDMA enabled NICs, and with the RoCEv2 being a UDP-based protocol, it's lossless Ethernet NICs, or lossless Ethernet switches are required for that, or highly recommended. Looking farther over on the right, what you see is a NVMe TCP with ADQ. We'll give a refresher on what ADQ is in the next slide, but basically it's optimized TCP, some optimizations that were put in for TCP to improve efficiency. The NVMe TCP, we're sort of putting this in a baseline IOPS as far as its CPU efficiency and its latency, because it's based on the traditional TCP stack. The RDMAs, they're the highest performance, highest and highest CPU efficiency and lowest tail latency, because that's pretty much what RDMA NICs were purposed for. For the TCP ADQ, what you see is high IOPS and CPU efficiency and low tail latency. So what's happening with ADQ, it's sort of closing the gap between the NVMe TCP and the NVMe RDMAs with some of the ADQ technologies. As far as the easy use, what you see is the difference really between the TCP and both the iWARP and the TCPs is standard network configuration, and because of the lossless Ethernet, what we're what there is, it's requiring additional network configuration. The usage model, which you see, TCP is pretty much a data center-wide transport, so that's a typical use case. It will accommodate that. With the iWARP, same thing. Rack level. Maybe because of the low latency, you'd put it more to rack level, but because it's based on TCP, it can go data center-wide. The RoCE, definitely rack level. With a lossless Ethernet domain, a bit more challenging to go data center-wide with a lossless requirement. And then the ADQ is a TCP based and data center wide. So the available open source stacks for NVMe over Fabric, there's actually two available. One of them being the Linux kernel, and what this is the NVMe over Fabric functionality resides within the kernel drivers. And that stack supports the RDMA, TCP, and TCP ADQ. So it supports all the transport, Ethernet transports. The other stack is a user level stack, SPDK. And what there is, it's the host and target are also both supported, but everything's up in user level. The difference between the RDMA and the TCP transports, if you look at the picture on the right, is the RDMA is taking advantage of the RDMA NIC kernel bypass verb libraries, that allow that user level application to directly communicate to the NIC through these or to the RNIC through these verbs. And then for the TCP, what you see is that the SPDK uses the kernel TCP stack. So the path through would go through the kernel into the, through a sockets API, into the kernel and have that processing done. What you can do, because these are all based on standard NVMe over Fabric protocols, you can pretty much mix and match. Like for instance, you can have SPDK hosts and Linux targets and vice versa. And then also you can there's a fair amount of proprietary targets out there too that both these host side stacks interoperate with.
So I'm going to give you, like Dave said, a short introduction on application device queue. It's a quick refresher. So there is a lot of existing history of advanced queuing and steering technologies on NICs. ADQ builds on it by bringing a very strong application focus to advanced queuing and steering. As shown on the graphic on the left, ADQ provides applications isolated and dedicated queue sets that essentially create express lanes for traffic to get to and from an application. With ADQs, you essentially reserve a queue set for an application. These are transmit and receive queues, configured typically as queue pairs. The identity of a queue is passed up and visible to an application. Each queue pair is optimized for a single producer-consumer model between it and an application thread. Additionally, you could also apply bandwidth control for egress traffic, and that can be used to shape traffic per queue set, enabling better bandwidth sharing between applications. One of the key things here is all of this is accomplished within the framework of the native OS networking stack, and there have been many contributions that have been upstreamed into the kernel that ADQ leverages. The table on the bottom right shows the ADQ capability suite, ranging from the bottom, from the NIC hardware through optimizations in the device driver and the kernel, and also if you want to optimize it from the application as well. So hopefully that gives you a quick refresher on ADQ, and I'll hand it back to Dave to walk through the next section.
Okay, the next section deals with the NVMe host side CPU efficiency of the transports. We're starting with this slide shows the basic model for NVMe, what the host side characteristics are for efficiency and what the contributors are. And basically, what you have is some of the contributors have to do with having per CPU thread submission and completion queues to avoid any kind of contention or interaction between the CPU threads. So essentially, the submissions for I/O are done on the same CPU thread as the completions come back on. And that's pretty much a common theme across all the transports of NVMe. Also, efficient completion models. What you see here is alignment of the interrupt, so that when that completion does come back on that completion queue for that CPU, the interrupt also goes to that CPU. That and also interrupts are moderated as the IOPS get larger, and that's true for the kernel stack. The SPDK stack that I showed earlier is a little different because user level, what that stack is based on is CPU polling. So instead of an interrupt, what they're doing is on a per CPU thread is polling the completion queue, but it still has that same submission queue, completion queue, pairing and affinitization. Also, part of this is the lightweight transport stack, so the ability to get those submission requests and completion queues back, and the data, you want that as lightweight as possible so that it's putting less CPU utilization on those CPU threads for the I/O operations. Then the final aspect that has to do with, okay, when I'm requesting either sending data, doing writes, or doing NVMe reads, I don't really want to be doing CPU copies of the NVMe data. I want that data to go directly from a buffer, out to the device or onto the network. And then as it comes back, we want that data to come right back into the application's buffer. And that's the zero copy semantics. Okay, if you look at PCIe, it was the first transport, and it pretty much has all these built into it. So what you see is, it has the per CPU thread, submission queue, completion queue, up to whatever the limit of the NVMe device is. Interrupts are aligned and moderated through MSIX and on a per CPU basis. There again with SPDK, these are polled, so there's no interrupts, but it's polled. The CQ is polled. Lightweight CPU transport stack and zero copy, yes, because the PCIe model uses a shared memory queue, so there is no, it's basically just copying directly, doing DMAs directly between the device and the buffers on the host. So if you look at this for RDMA, these same contributors, what you see is with RDMA, the mapping was defined to have the submission and completion queues mapped directly onto an RDMA queue pair. So there again, it's paired, and that queue pair is aligned with the CPU thread. So if you have multiple queues, what you see is each CPU thread would have one of these queues. The interrupts associated with that are aligned, so the interrupt on those RDMA queue pairs come back on the same CPU that the submission was mapped onto. Again, polling for the SPDK, so it polls the RDMA completion queue that's mapped to the submission queue. Lightweight transport stack, the RDMA NIC actually has the transport stack in it, and it uses that, for instance, either with the UDP with the RoCE or with the TCP with the iWARP, and it provides a very lightweight interface called verbs, is how the NVMe RDMA transport talks to that RNIC hardware. So it's very efficient in that sense, and the fact that stack is offloaded. Zero copy is achieved through the RDMA read and write operations that allow the buffer address to be passed to the NIC and that data to be sent, directly on the ingress directly into a buffer, or on the egress, have that buffer directly taken from the buffer and out onto the network. So if you look at TCP, what you have is the definition, the NVMe over Fabric TCP transport definition, and has that the submission queue and completion queue are mapped onto one-to-one to TCP connections. So that gives you your alignment. The interrupts are based on kernel and NIC hardware flow steering logic. So typically when something is sent out on a specific TCP connection. In this case, if it's sent out of the submission queue that's mapped, it'll come back on the completion queue with that on that same TCP connection, and it'll end up on the same CPU thread. For SPDK, it uses a socket level polling because the sockets is the interface that it's using to get to the kernel TCP that I showed earlier. So what you see here is instead of interrupts and such, it'll be polling that socket to see whether any data has arrived. In this case, the transport stack, because it's in software, it's heavier than what I showed with the RDMA or the PCIe, because it is a software stack, and some of the efficiencies are achieved through sort of generations of NIC TCP hardware offloads. So there has been multiple years of work to get TCP sends and receive efficient, but it's not a full offload like the other two that I showed. You see a zero copy on transmit through the use of, at least on the kernel, through the use of a send page operation. On the reception, because the packet comes in, without any identification of where the data goes, you'll see a copy from the packet buffer into a user application. So there is a copy on the reception. Okay. So with the ADQ, what's happening is there again, it follows the same model with the TCP connections being mapped. Some of the interrupts moderation, it's more enhanced than what you see for the TCP stack. And also there's optimizations, busy polling. And what you see here is the busy polling is optimized such that instead of waiting for interrupts to come in, there's ability to poll down at the lower level in order to reduce the latency of having to wait for that interrupt to come in, essentially. So it's sort of as the load gets higher, you see that taking place. It reduces context switch as well. Part of the overhead, if you look at the the reception of packets in the systems, is the multiple context switches that take place along the packet processing up to the application. So ADQ has some techniques that Anil explained that essentially optimize that. The other aspect of it, I showed, the NICs have, with this ADQ, have the ability to have dedicated hardware queues that allow those hardware queues to be associated with the NVMe CQ mappings, such that you don't have multiple packets, that are mapped to multiple TCP connections, mapped to multiple, NVMe queues that the software has to essentially, unravel. So this allows that queue to be serviced, in the context of that TCP connection. And then the same, because it's TCP, it's still, zero copy on transmit and then a copy on reception.
So like Dave said, let's dig a little deeper into the TCP, NVMe TCP transport and the specific ADQ efficiency optimizations that are brought to bear on it. The table shown on the slide provides some more details on these optimizations. So like was mentioned earlier in the ADQ introduction, ADQ provides a dedicated and isolated queue set, in this case for NVMe over TCP. This ensures that only NVMe traffic, NVMe TCP traffic, gets steered to this queue set. Specific queue identification within this queue set enables the NVMe worker thread to align with a hardware queue, creating essentially a single producer-consumer model between a queue and the thread for all the traffic that is being handled by the thread. The benefit of this is that when you have these dedicated queues, you significantly you're not sharing them, and so that reduces jitter. And also, since these queues are dedicated, this enables some targeted application-specific queuing optimizations. So along with the queues that are dedicated, there are some additional optimizations in the driver, for instance, to facilitate better queue steering and signaling to the chosen queue set. The signaling is key because in conjunction with busy polling, one can be pretty aggressive and with how interrupts are moderated. And so these optimizations in the NIC help reduce jitter and latency and also improve throughput for NVMe over TCP. Egress rate shaping, this provides a hardware accelerated bandwidth or traffic shaping for egress traffic. Now this is maybe optional, but for some usage scenarios, one might consider partitioning the bandwidth amongst different applications. And so you might then choose to allocate bandwidth per application, and that's handled through hardware acceleration. And you can, for instance, say that, okay, I've got 100 gig NIC and I want to dedicate 60 gig for NVMe traffic and 40 gig for something else, as an example. Socket priority, this sets the socket priority that is used to this sets the socket priority that is mapped to the hardware offloaded queue. So when you first configure ADQs, you allocate a queue set and you also allocate a priority with that queue set. So when a socket priority is set for that queue set, it enables steering these packets to the correct isolated queue set for transmit or egress. And also within the queue set for an aligned TXQ of the TX-RX queue pair. The advantage of this is that it reduces jitter. One of the problems in the first implementations of the NVMe over TCP drivers was there were multiple context switches that were occurring in the submission and the completion path. So with some of the work that has already been upstreamed, we are now able to perform requests and responses in context, meaning that you don't incur a context switch for a request and a response. So that allows you to process the request and the response in the context of the application without actually switching context out of it to the IO thread. And obviously, when you reduce context switches, you generally reduce CPU utilization as well as you significantly reduce jitter. Busy polling is a key part of getting significantly low jitter and minimizing context switches. So busy polling here allows, queue draining, because the context switches are gone. It allows you to drain the queues and reap your completions directly from the application context. In this implementation, for instance, it leverages the IOU ring for instance, for the kernel host. And if you're running a user mode, user mode host or user mode target, you could leverage ePoll and socket system calls to initiate busy polling. The obvious advantage of that is, of busy polling rather, is that it reduces jitter, context switches, latency, and also improves throughput. Last but not the least is this notion of grouping, where you group multiple NVMe TCP queues to a single NIC hardware queue. allowing more effective sharing of NIC queues. For example, polling can then handle requests from multiple NVMe TCP queues to improve the throughput on a core without redundant context switches. And this, in effect, reduces CPU utilization and latency. So hopefully this gave you, flavor for the types of optimizations that are in play, and these optimizations are applicable both on the host and the target.
Okay, with this slide, what we wanted to show was the host side efficiency measurements of the transport options that we described. And what we did before this test was essentially put the host side single CPU at 100% utilization, with a random read workload. And so what I'm showing here is the blue is the kernel host implementation, and then the orange is the SPDK. So what you're observing across, pretty much for both the TCP and TCP with ADQ, what we're seeing is, for both SPDK and kernel is an efficiency improvement that ADQ brings into play between for the TCP transport. If you look on the right, excuse me, the blue is the in-kernel RDMA, and one of the reasons you see a big difference between this blue RDMA and the SPDK RDMA is really because the SPDK RDMA is happening all in user level. It's plugged in. The FIO has a plugin that goes directly to the transport, and the verbs go directly through. And it's the highest performance, but it sort of comes with some caveats that because it's all user level, it has some of the usage model, like for instance, if you were to put a file system in there, that file system would also have to live up in user level as well. So not all applications can take advantage of it, but for those that do, it's definitely the most efficient. So what we want to cover next is moving from the host side over to the target side, just to look at the efficiency on the target side of these transports. Excuse me. So the target side efficiency, what we do is we looked at the two open source targets for this, and really look at some of the common methodologies that were used to essentially be able to scale the target up to support multiple host systems. So it's really around, okay, how can I get the most efficiency out of the CPU threads and service the most queues that are spread across the most host systems out there on on the network. And there again, here it's the same thing, where we have CPU thread submission and completion queue mappings, keeping those localized so that you're not having to have submission requests and completions have scattered across different CPU threads. Some of the techniques as far as the interrupt and polling scheduling techniques, essentially spreading the interrupts around across the CPU threads so that they're not sort of oversubscribing CPU threads. And same with the polling. Some of the polling techniques have to do with sort of optimized polling of groups of connections, either an RDMA or in the case of TCP, it'd be TCP ADQ polling for a group as opposed to polling for a single one is some of the techniques that can be used. There again, lightweight transport with queue separation. If the target's doing transport logic, you want that to be as light as possible so that you can be doing the storage logic on the back end of it. And then efficient distribution of multi-host queue, on the target side threads, as I mentioned before. So if you look at the RDMA transport, what you see here is the submission completion queue mapped onto the RDMA queue pair, and the distribution of the RDMA completion queues vectors across multiple target CPUs, so that you essentially are spreading the load across, for the different NVMe queue pairs across multiple CPUs in order to get sort of a good distribution. In the case of RDMA, it actually uses a polling technique and has the inner moderation of the RDMA NICs is fairly conservative in a sense, that it through the use of event queue it does good moderation. For the case of the SPDK, what it's doing, it doesn't use the interrupt. So what you see is those CQs are polled. So the CQs are grouped into groups that each of the CPU threads would poll that group, and such that it avoids the overhead of having the interrupts. The lightweight transport stack, again, this is hardware offload of the capsule and data transfers. All the reception and completion and the data, NVMe data with the RDMA is all handled by the RNIC hardware in an offload fashion. For the SPDK, the kernel bypass is used because the SPDK is a user level target, so there's no kernel interaction in this with the RDMA transport. Okay, for the TCP, what you have, same thing. It's same as I mentioned before, that you have the pairing of the TCP connection, and then again, it's optimizing that IO thread alignment with the TCP connection itself. Is some of the NICs which you're looking at is, depending on the type of what the NIC hardware has, you see fairly aggressive interrupt moderation. Such that multiple packets coming in on the queues, you're not getting an interrupt per packet. You're getting interrupt through some number of packets, and if you're busy processing the queues, the interrupts are moderated such that it realizes that the software is busy essentially. Lightweight stack, what you see here is this is a standard TCP socket service mechanism, and so. At the case of the, for TCP, what you're looking at is sort of packet level optimizations, with some of the stateless offloads that exist in the NICs, like the large the TSO, which is large send offload, and large receive offload techniques, for the bulk transfer type operations.
So from NVMe target side, CPU efficiency, when you're looking at it, but with ADQ, what are some of the efficiencies that we have on the target side? Essentially, for the thread to CPU mapping, the thread to SQ-CQ mappings, we are doing this mapping by having the dedicated queues that we work with, and the optimized thread alignment allows us to align the IO thread that is servicing these NVMe requests, align them with the queue set, and in particular a queue within the queue set. We also, in order to be more efficient, we also have the ability, and with grouping, where, like I mentioned earlier, we can group multiple NVMe TCP queues to a single NIC hardware queue, which really allows effective sharing of NIC queues, so that, for example, when polling is in play, it can handle requests from multiple NVMe TCP queues to improve throughput on the core. As far as interrupt and polling techniques go, so the interrupts, we have some aggressive mechanisms because we have dedicated queues, and these queues are solely dedicated to NVMe over TCP, so we don't have any dependencies on sharing, which is one of the advantages of having dedicated and isolated queues. So you can put very targeted tuning for things like how you would deal with interrupts. And polling here, like I mentioned earlier, polling is hooked in through the is in play, and packets are polled from the NICUs using busy polling sockets. As far as the lightweight transport stack goes, I mean, there is efficient busy polling, and it is per group, and we're able to align a connection group per NIC hardware queue pair. So this alignment, again, the basic idea here is that when you have this alignment in place, you are more efficiently processing, connections that are coming in to the target from multiple initiators very efficiently on a given core. So in order to facilitate that, we also have some efficient load distribution schemes for distributing the load amongst the queues in the particular queue set. So we wanted to show a sort of a representative target and shows performance associated with the target. Now, in this case, what the slide is showing is the SPDK NVMe over TCP target, and on the y-axis, you see, the IOPS that's the IOPS delivered by the target, and on the x-axis, you see, how it scales based on increasing cores on a given platform. And what you can see here is that we're able to get to the wire rate of 2.8 million IOPS with, in this case, 5 cores on the platform, which is, pretty impressive performance. And if you look at the secondary y-axis, it shows the average latency as shown by the lines on the chart. If you were to compute, the percentage improvement, what you're seeing is that you're able to get, approximately at the high end in terms of IOPS, about a 33% improvement in throughput, and for the average latency, when you compare it with baseline NVMe over TCP with SPDK, you're about 23% lower in latency, so you get a 23% reduction. So in essence, ADQ shows substantial performance improvement to the SPDK NVMe or TCP implementation. And just to round it up, the details are shown here in terms of what the queue depth was and how many connections per target core. And this was done for 4K random reads with an MTU, standard Ethernet MTU of 1500 bytes. We also wanted to show how ADQ improves predictability. One of the key aspects of ADQ is improving predictability, and predictability is very important for workload scaling, especially as you scale out. So if you look at performance, most people are very interested in knowing not just what the average latency is, which was shown in the previous slide, but also specifically what the P99 latency is and the P49 latencies are. Those are something that increasingly people are caring about, because it impacts their ability to scale. So as you can see in this picture, you can see the same data that was plotted in the previous one in terms of throughput and average latency. Here it shows the P99 and the P49 latencies for ADQ and baseline. And you can see here, for instance, that at its peak with ADQ, where you were getting 2.8 million IOPS per second with 5 cores, the P99 latency is, in this case, 262 microseconds, which is a really good number at P99, and the P49 is 322 microseconds. All these numbers are, way below what traditionally, one is accustomed to seeing for P99 and P49 latencies, because there's, because of a lot of the work that's gone in to tune the stack and improve the performance through the various optimizations that we spoke of. So in essence here, ADQ reduces tail latency substantially across different configurations. And like I mentioned earlier, this is for the same configuration of 4K random read 1500 MTU and QTIP32 with 3 connections per target core. So to conclude, hopefully this presentation gave you an overview of the various NVMe over REV transport options available, and where they might make sense depending on the specific network storage requirements that a particular deployment may have. The NVMe over Fabric host side performance for all the kernel transports is more or less similar, as you saw in the graph that Dave described. And they've also described the SPDK NVMe RDMA offers the highest performance when that is in a deployment that it is applicable to. Then we talked about the NVMe over TCP transport with ADQ, and you can see that for TCP, when you have ADQ enabled, you see a significant improvement in performance, both in terms of throughput and in terms of average latency, and also in terms of predictability, as we showed in the chart just before this one. So if you want to know more information, there are a few other sessions and related sessions where you can actually get a deeper dive into some of these optimizations and assists. So there is a session on optimizing user space NVMe over transport solution for both software and hardware, with both software and hardware optimizations, and that one talks about will talk about more details on SPDK and the flow, and also has references to ADQ. The improving NVMe TCP performance by enhancing software and hardware is another session where there's more detail on the flow of the stack and what it looks like, and some of these optimizations in more detail. And if you want to know more about ADQ, you can certainly visit www.intel.com/ADQ and look for more material on ADQ. So with that, we come to the conclusion, and please take a moment to rate the session. Your feedback does matter to us. And thanks for listening.
Thank you.